Hey everyone, Mr. Shakti here to talk about section 7.3, which is volume. Objective of this video is to calculate the volume of three-dimensional solids using the disk and washer methods. To get started, let's look at these pictures. On the left, we have a couple of curves, and these curves are intersecting, creating a region, and in section 7.2, the goal was to find the area of that region. Well, in the middle picture, what we're doing is we're taking that purple region and we're revolving it about the x-axis. So that in picture 3, we have a three-dimensional solid left over. In that three-dimensional solid, the goal is to find its volume. In order to find the volume of this three-dimensional solid, what we're going to do is we're actually going to take one of many slices. Okay, here's just the outline of one of the slices. Now a slice looks a little something like this. All right, this is just one of these. If you pull together an infinite number of them, you create that three-dimensional solid. Key volume note number 1, draw a picture of the region. Number 2, always slice perpendicular to the axis of rotation. That one's very important. Number 3, figure out if the slice is a disk or a washer, which we'll talk about in a little bit. Number 4, draw a picture of the individual slice. And number 5, ignore the reflected image when calculating your radii. Only consider the original. Okay? There are two types of slices you could have. You could have a vertical slice if the axis of rotation was some horizontal line, because we always slice perpendicular. If you're doing a vertical slice, your equations need to be in y equals form. You need to do a top minus bottom to get the distance, and your limits are your x values. If you do a horizontal slice, so your axis of rotation could have been something like the y-axis, you have to slice perpendicular. Your equations need to be in the form of x equals. You do a right minus left to get the distance, and your limits must be y values. Okay? These are just a couple of tips about a big radius and a little radius that will apply when we're talking about a washer. To get a big radius, you have to go from the center of rotation, okay? This should say center of rotation to the outside of the enclosed region. In the little radius, you go from the center of rotation to the inside of the enclosed region. And I'll show a couple of pictures in a minute about what that means. I just wanted all the notes to be on one slide for you. So, in order to find the volume, what we're going to do is take the area of each individual slice, which, since they're always going to be circles, will always be pi r squared. Okay? And we're going to multiply that by the height of the slices, which is just in our case going to be dx or dy. And in order to find the volume of the solid, we're simply going to integrate that formula from a to b, which is going to be the bounds of our region. So the first situation you could have is a disk. Now, you have a disk, I'm going to change my color to blue, when the region that you're revolving is snug up against the axis of rotation, meaning there's no open space when you revolve this region. So notice the triangle's not like, up here or something where you have this extra space or gap. The region itself is snug up against that axis of rotation. And what that does is it just creates a closed circle known as a disk. And the nice thing about a disk is it has only one radius. In order to find the radius of a disk, you put your pencil on the axis of rotation. So the axis of rotation is right here, whatever you're revolving about. And you sketch all the way until the end of the curve. That distance is known as r. And the nice thing about disks is the value of r is typically the curve. In this case, the value of r would be 0.5x. And the second situation is a washer. We already saw a picture of what a washer could look like. You get a washer when your area that you're revolving is not snug up against the x-axis. So for example, take this triangular region. What if we took this triangular region and we revolved it about the x-axis? Because there is a gap between the curve and the axis of rotation, that's going to be that inside circle that I'm highlighting, but it's just shading in darker. I'll highlight it over here. That inside circle over here, that's a hole. We don't want the area of that to be included. Because of that, we're going to have to adapt our formula a little bit over here. So in order to find the area, you're going to actually have to find the area of the outer circle and subtract it from the area of the inner circle being the area that we don't want, the empty open space. So whenever you do a washer, you're going to have two different radii. So the first one we usually call little r. So to find little r, you put your pencil on the axis of rotation, so that's in the center, and you basically start tracing until you bump into the region, okay? So if I were doing, in the bottom in this picture, if I were doing this right here, I would start here, and I would stop right here when I bump into the region. This distance would be known as little r. Big R, okay, is when you start from the axis of rotation and you go all the way to the end of your area. That distance is known as big R. The area of the slice is just equal to pi big R squared minus pi little r squared.